Water, water everywhere, with less and less to drink. From space, the Earth is a big blue planet, covered 70% in water. But a closer look reveals that only 2.5% of that is fresh water, with only 1% being easily accessible to keep our 6.8 billion inhabitants alive and well. A United Nations report suggests that water consumption has grown twice as fast as population growth. By 2025, it's estimated that 2/3 of the population will live in water-stressed regions of the world.
Water scarcity is a serious problem globally. It's been said that there'll be wars fought over water.
This is TechKnow, a show about innovations that can change lives. We're going to explore the intersection of hardware and humanity, and we're doing it in a unique way. This is a show about science by scientists. When it comes to water scarcity, part of the problem is that our modern world was built with little concern that water is a finite resource.
Our society, our economy, our whole system of living was based upon a paradigm of plentiful water. And I don't think it was considered, oh, what if we need to use less?
Especially in agriculture, the pressure to feed the world uses most of the freshwater supply. 69% goes to farming, with 19% going to industry, and only 12% to households and municipal use.
I think we are unintentionally wasteful with water, but we use more than we probably need to in an ideal situation. But a part of it is relearning how to use less water.
So with a global freshwater crisis upon us, scientists like Dr. Daniel Fernandez are working to create innovative solutions to help save our stressed freshwater supply. We begin in California's Central Coast, where scientists are looking up instead of drilling down, capturing water from a weather phenomenon that's been around for millions of years.
Fog is a crucial part of the ecosystem, and it's a very interesting, intriguing part of a very complex system that we call weather, and it's one that is much less understood.
I'm on a research hill in Monterey, California, and what's really interesting is the contrast between old and new technology. On one side of me is a field of solar panels, which is having a huge impact on the way energy is consumed in the local area. And then behind me is the age-old technique of collecting water from fog, which could provide a solution to the problem of global water scarcity. This seems to be a very novel technology, but it's actually been around for a while, hasn't it?
Fog collection actually has been around for a long time, longer than, in some cases, recorded history.
So how long have humans been trying to harvest this water?
You can see evidence even 10,000 years ago in areas in Chile where some of the populations there actually established their bases, and we know it from archaeological evidence where middens were found, happened to be in locations that were heavily fogged areas.
The idea may be from the past, but the science behind it is new.
All right, and I'll grab the tools. There's the afternoon breeze. So we're gonna be, I think, more on this side.
Dr. Fernandez and two students carry up the parts that, when assembled, will become a research fog catcher. A half hour later, it's almost ready to collect data with 2 fog nets already deployed.
So why have you chosen 3 meters in between them?
Because I want to have significant enough separation that one of these fog collectors won't affect what the other one is picking up.
We're going to anchor them down?
Yes, now we're going to anchor them down. We want them to be pretty steady.
This is really engineering at its best. I'm standing here with metal pipes in my hand and a mesh net above my head, which hopefully is going to collect water from fog. And it's quite foggy right now. Is this typical, or are you expecting more fog?
It's not going to catch any fog in this weather right now because the fog's up a couple of 100 meters. The fog literally has to be right where we're standing. And that typically is going to happen during the night and in the early morning hours before the sun comes and burns the fog away.
So another data point goes up.
Exactly.
What's being studied here is how to create the most efficient fog-catching device. At the heart of it, innovative mesh designs, some made of plastic. to capture the maximum amount of water possible.
And what we're experimenting with are different amounts of mesh, and the standard is to use 2 layers. So we're actually collecting data on 1, 2, and 3 layers to see which one really does work better.
Innovations in mesh design come from what scientists call biomimicry, building on what Mother Nature has already created. In this case, taking cues from leaves that collect water on trees.
Can we emulate the surface of the leaf? Keep in mind, a leaf has a lot of different surfaces, different angles. There's a lot of complexity in the surface that the wind can blow through and the little droplets of fog can collect on. So one example is here. This is a type of mesh that is actually made in Chile. It's called a Rochelle mesh. And a double layer of it is the standard type of mesh used for fog water collection. And you can see there's actually different surfaces involved in this mesh at different angles. And in a sense, this emulates what a tree would do.
The structure of this mesh must be crucial.
That's one of the things that is a current area of research. What is it about the mesh that makes it an ideal fog collector? There's a lot of interest in what type of materials make good fog collectors. Is it the physical characteristics of the mesh? Is it perhaps the chemical characteristics of the mesh? We're still exploring what are all of the details associated with optimal fog collection under different environmental conditions.
This seems like quite a small setup, but how much water can you collect typically?
You know, in a standard day around here, we might get, during the fog event, a fraction of a liter. But there's some areas where we have some elevation where we get fog. In some cases there, I can get several gallons in a day.
What if you were to scale this up and have giant meshes? You know, that would change everything, wouldn't it?
Yeah, there are places in the world where they're doing that, including Morocco, for instance, Eritrea, Chile, Guatemala, Haiti. So there's a number of countries around the world that have fog, that also have serious water needs, where they are scaling these up. So they have fog collectors like this that are dozens of square kilometers in size that collect correspondingly that much more water because they have the area.
So how many nets are developed around the world at this time? FogQuest, a non-profit organization involved in sustainable water projects, estimates that currently 200 fog collectors in 10 countries are producing 40,000 liters of water a day. An example of this is found in South America. There isn't a tree in sight in the harsh Atacama Desert of Chile. Stretching almost 1,000 kilometers, it's known as the driest place on Earth. But because it's located near the Pacific Ocean, the region is blanketed in a daily dense fog known as camancaca.
Parece que cuando baja la mar y sube la mar, azota más y el viento del sur-oeste se lleva la parte húmeda del agua del mar.
Villagers have turned to a system of simple nets to capture water from fog.
Puros cables. Y colgamos las mallas nomás y le ponemos hacemos un hoyo con una y hacemos el hoyo y listo.
It's a much simpler version of the fog nets that Dr. Fernandez is studying and innovating in California. But for the people of this desert, it delivers a gift of life.
Y la canala la llevas a través de una manguera que va bajando por la ladera del cerro y llega a los estanques de acopio.
The nets capture about 10,000 liters of water a day from fog.
Esta agua viene de 620 metros de altura y viene cantando cada 100 metros.
And the fog water is used to bring new life to the area.
Está acá. Esta agua va para ir alimentando a las beberas.
For the people of Chile who see this simple water source as a gift from nature, they don't concern themselves with the chemical makeup of what their nets have captured.
Yo lo encuentro espectacular. Yo lo encuentro espectacular, de verdad. Nieblina, nieblina, bendición divina.
Back in a laboratory at the University of California, Santa Cruz, Dr. Peter Weiss-Penzias is conducting research on the safety of using collected fog water for irrigation and human consumption.
As a chemist, I came into fog from the point of view of wanting to know what are the chemical compounds that are present in fog. And by its very nature of being composed of very small water droplets that are suspended in the air, it's very efficient at absorbing particles and gases. And particles and gases often include toxic, noxious compounds that have been released by human activities, or in some cases, natural sources.
And unlike raindrops that fall to the ground very quickly, fog droplets can be suspended in the air for hours or even days, absorbing a variety of pollutants and compounds.
Places like eastern China, Shanghai, Japan, various cities in Europe, they have heavy smoke, lots of aerosol particles, heavy metal toxins such as mercury in the air, and these can be absorbed and concentrated into the fog droplets. The droplets then can strike vegetation or maybe the surface of a building and deposit those pollutants onto the surface where they would then be exposed to them.
Your studies have led you to measure methyl mercury in water. That sounds incredibly worrying that it even exists.
Methyl mercury could be formed in deeper waters of the ocean, and then through coastal upwelling, which is a process that brings the deeper water to the surface along the coast, especially along California, that methylated mercury could come to the surface of the ocean, and it's volatile as a gas, so then it could escape the ocean water and possibly be taken up by a fog bank. And sure enough, we found that they contained roughly 10 times higher methyl mercury than we typically find in rain. Now, should we be worried about it? Still, the levels are very low. It would not be harmful for humans to inhale the fog water and absorb that methyl mercury because the health threshold is still probably 100 times greater than what we see in the fog.
But what about the more pristine parts of the world collecting fog water, like we've seen in Chile?
As far as we know, their fog water is fit to drink.
Would you drink the fog water collected in Chile?
In Chile, I probably would, yeah.
So you have some samples of fog water here, don't you?
Yes, these were collected on some very foggy nights here at UC Santa Cruz. I wanted to show you a simple test that we could do, and that is pH. And so what I have here is just a small amount of the fog water. The fog water just came out of the air, and we'll compare that to some tap water. And this is the kind of really the most basic test that you'd want to do if you were to determine if the water was safe for drinking or for irrigation. And so for the tap water, we would hope that the tap water is close to neutral pH. So let's go ahead and test that one first. So we'll just stick this little pH strip in there, and we compare it against our scale, and it looks like it's, there we go, and it's about 6, and maybe slightly more than 6. So neutral pH is 7, tap water is about 6, so that's good. Now we'll test the fog water, and if we were collecting this fogs in a very polluted location near maybe some coal-fired power plants, that the sulfur released from those emissions would create sulfuric acid, and this would be very acidic. But fortunately here in Santa Cruz, we don't have any such industries, and so now we'll measure the pH. Now let's compare the two. We've got the tap water here on the right and the fog water on the left. I would conclude, at least from a acidity point of view, that the fog water would be safe to drink or to use for irrigation.
Irrigation and agriculture, the largest draw of freshwater usage on the planet. We saw how fog can help on a small scale in regions like Chile, but how could it impact the larger agricultural picture around the world?
In agriculture, for instance, there's people who are currently looking at, can we water intelligently? In other words, can we choose to water when the crops reach a certain level of dryness, rather than just watering on some sort of a schedule?
Fog can augment water availability during the otherwise dry time of year and offset water stress.
On this strawberry farm in California's Central Coast, Dr. Sarah Boguskas is scientifically quantifying the balance between fog and irrigation.
Essentially, knowing more about fog could actually change the way we water crops.
Yes. It changes the physical environment in important ways that reduce what's called evapotranspiration. Evapotranspiration is the loss of water from the surface to the atmosphere from soil and plants. On days like today, evapotranspiration is reduced. If the plants aren't demanding as much water, you don't need to irrigate as much.
This sounds like common sense, but collecting the data to formulate an overall watering strategy is being done for the first time.
There's a big gap right now between the information that this research is generating and farming practices. This research is the first to address how coastal fog events impact evapotranspiration rates and crop function.
Dr. Baguskas's research begins with a series of scientific instruments measuring plants at ground level.
These are some of the instruments we use to measure the exchange of carbon and water and energy between the atmosphere and the surface.
Is there a particular reason why this instrument lies in this particular spot?
This is an ideal location, actually, to really understand coastal fog influence on ecosystem level carbon and water balance, because as we can see, it's a pretty homogeneous landscape vegetatively. There's not a lot of noise associated with the effects of different species or topography on these changes in concentration. We can really cleanly understand the effect of coastal fog on field scale carbon and water exchange.
What is this device here? It's making a lot of noise.
So this is what's called the Lycor 6400. It's a portable photosynthesis system. And this instrument allows us to take the pulse of plants at the level of the leaf. When we clamp this instrument onto a leaf, which you're welcome to do, we can measure how much the leaf is photosynthesizing and transpiring. So how much carbon it's taking up and how much water is leaving the leaf. So why don't you clamp on it and
Let's see how it does.
And just go ahead and clamp all the way and hold it there. We're observing right now in real time the rate of photosynthesis and what's called stomatal conductance. So that's the degree to which the pores on the leaves are open or closed. So the larger the number, the more the pores are opened, and that means that there's more water loss.
What is this data telling you overall?
This is really the heart of the project. We want to have a mechanistic understanding of how these crops respond to their environment. And so the data that I've been collecting using this instrument tells us that plants don't lose as much water on foggy days compared to sunny days. So there's a significant reduction in water loss from plants on foggy days.
I have to say that sounds very intuitive. You know, you would expect them not to need so much water when it's foggy. So why is your research so impactful?
This is the first time that we've been quantifying it, understanding what the effect is on fog and being able to compare and contrast the response of crops to different environmental conditions. If this instrumentation could be used in a variety of different ecosystems and agricultural systems around the world, we'd have a much better understanding of how local climate affects water demand from farms and have much greater potential to confidently make informed decisions about how much water to apply in agriculture.
Reducing irrigation amounts in both fog and other farming regions is yet another small step in addressing water scarcity. From fog, farm fields, and deserts around the world to an exclusive hotel in Los Angeles, California, the quest to address water scarcity through science and technology continues. Here with more on that part of the story is TechKnow's Costa Grammatis.
The Hilton Hotel in Universal City, California is no stranger to doing laundry. Every room uses 25 gallons of water a day to keep the sheets clean. However, thanks to some new technology, all that has changed. Beneath the bustle of this massive hotel, inventor Steve Jenkins, the chief technology officer of Xeros, a London-based company, is making a dent in a world thirsting for more of one of its most fragile resources, water.
So at the moment what's happening is things are tumbling around in the drum, they're just being sprayed with water and detergent.
So far, this Xeros machine looks like any ordinary commercial washer, but then comes the water-saving innovation.
We use so little water, we've got to put this pre-step in to spread the detergent nicely before we start. And then the beads are going to come in and do their wash.
Polymer beads, around 1.5 million of them, taking the place of water in the washer. These beads act like tiny sponges, pounding, soaking up, and carrying away dirt and stains from fabrics.
So once the beads have actually dropped in, they'll start tumbling, and then there are holes in the drum wall, and the beads will actually go through that, fall down back to the tank, be collected, and then pulsed back up. So all of the beads go in, and then some of the beads are pulsed around just to keep it topped up as we go through the wash cycle.
So there's less water used in a conventional washing machine of this size?
Typically 80%. So in our cycles here, we're using 115, so 115 litres of water.
Okay.
And that's really low for a 25 kilogram wash load, really,
What
really
are they usually?
low. Typically, you'd be 500 litres or even more than that, we've seen certain examples of. So we're saving a lot of water, and we're cold, and we're washing with a lot less detergent. So it's a really sustainable process.
A simple chemistry demonstration offers a close-up look at how the polymer beads work.
Blue from Gene?
This is blue dye. It's just a solution in water.
Yeah.
It's moderately warm. It's only just above room temperature. But you can see that that's just the dye that we've made, that dye that will be used rather when we make those jeans that you're wearing there. Okay, and this is the beads that we're going to test. And these beads basically slightly bigger. You can see them better at the camera. And they're also the next generation of beads that we're working on with BASF.
These are going to replace those little beads?
These are going to move and replace those beads. Okay, so if I just fill this up with this lovely solution, and we're going to put this lid on here so we don't all get covered in it.
Okay.
And then I need a happy volunteer.
To give it a shake.
Who's going to shake that for about 2 minutes. Okay, so what's happening in there now is those beads have chemistry in them as well as the polymer. There's more chemistry in there, which is actually starting to absorb the dye in the system. And the beads will gradually turn bluer and the water will actually turn clearer. And it will take about 2 minutes from now.
It already looks gray. That's amazing.
So you're seeing some sort of turbidity, some haziness in there. That's just from the action of the shaking and the foaming and the frothing. That will settle down.
Okay.
But the colour change is the important thing.
I'm basically being a washing machine right now.
You are being a washing machine.
And what makes these the second version?
So the size and the shape's different, and the density is slightly different.
Yeah.
That's to help us get more of the beads out of the wash load.
Yeah.
And get a bit more mechanical action into the wash, so a bit more mass to the bead. Fewer beads, obviously, because we don't want to put the volume up. We keep the same volume in the machine of beads, but we've got fewer beads. Okay. So we started out with this colour.
Deep purple.
And this is what we end up with, so.
Wow. So
you can see the colour protection effect there.
That's amazing.
And you can also see the effect on the beads.
The beads just sucked it all up.
Correct.
Could you use a mix of beads that are tuned for each individual color?
You can. And you can put different chemistries in the different beads. A complicated solution, but it's technically possible.
Unlike water that is used in commercial and home washing machines and later discarded, when the polymer beads have reached their full life cycle, after hundreds of uses, they're not just dumped into local landfills.
And once we've taken those beads away, of course we don't throw them away, we either clean them up and we can potentially reuse them in the system, or if they're beyond that, then we can recycle them into other applications.
Are they just melted down?
It can be melted down and processed just like plastics of this type are generally anyway, and made into different things.
These machines are catching on in North America and the UK, with hundreds of models up and running. But the biggest consumers at the moment are hotels.
This machine here is saving over 72,000 a year.
Wow.
So that's a lot that's being saved from low water, low energy, low chemical, and that's the benefit our customers pick up directly, annually, with 3 machines.
a technological advancement that not only saves money, but more importantly is having a quantifiable impact on conserving fresh water through innovation. Just one more small but important step in scientific efforts to help mitigate water scarcity around the world.
That's all for today. Join us for more science and innovation from around the world next time on TechKnow.